All right, so if an object displaces a weight that's equal to, of water, that's equal to the weight of the object, at that point it floats. And so this kind of revolutionized our ability to be able to build ships, because it used to be thought, and they did a good job of building ships thousands of years ago, but they always built them out of wood. And the reason why they did that is that wood floats. And so they figure, well, if you want something that floats, you got to make it out of objects, the material that floats also. But we discovered that that's not the case, as you can make aircraft carriers out of metal. And as long as the metal can displace enough water to equal the weight, then you can have an object that's made out of metal floating in water. And you can also have, in the air, you can have the similar kind of thing with, say, a blimp. A blimp basically has lighter than air molecules in it, and so that is displacing a weight of the atmosphere, and that gives rise to an upward buoyant force on the blimp. Okay? In just the same way as a boat can float in water, a blimp can float in air. And so those are all different examples of how we can use the principle of buoyancy to our advantage to get one object to float on top of another. Now, if you add more weight to this, then eventually you get to the point where the water starts slurping in. And so that's your limitation then, is when the total weight here is such that you need to keep displacing more and more water, eventually the water level gets to the point where the water can add to the mass inside and the object sinks. And so that is your limitation. But now here with case 2, let's say that the object already has a density that's greater than water, and it's a solid object, so that it's not displacing any water with a lighter substance, okay? But rather all the water that it's displacing is associated with a heavier substance, and so that's an object then that sinks, has a density here that's greater than the density of water. So let's say the density of our metal is equal to 5 times the density of water, or that would be 5,000 kilograms per meter cubed. That's also the same thing as saying that it has a specific gravity of 5, okay, because specific gravity is measured in terms of how the density relates to the density of water. And so we have something here with a specific gravity of 5, or in other words, 5 times the density of water, and it's sitting in a container of water. Now, let's see if we can find what the apparent weight is. What do I mean by this? Well, I simply mean how much does the object appear to weigh in the water? And it's going to be lighter by the amount that's equal to the buoyant force. So here's our buoyant force. It's going to act upward, but this is no longer a situation where the buoyant force equals the weight. But rather, the buoyant force just lightens the normal force. Okay? And so there is a normal force in here, but if you try to pick it up, then you're taking the place of the normal force in being able to lift it. Okay? And so finding the apparent weight then of this cube would require that we know what the dimensions of the cube are. Let's say here that L in each case is equal to 2 meters. Okay, so in other words, this is 2 meters by 2 meters by 2 meters. Okay, and so we can say then that the apparent weight is the true weight minus the buoyant force. And so that's what we're looking at then here, is an expression for the apparent weight in terms of the true weight, but then subtracting away how much lighter it seems to be underwater. And so what's the true weight? Well, the true weight, remember, is density times volume as mass. That's the density of the metal times the volume of the metal times g. Okay, so that's mass, density times volume. Just drill that in. Total mass is density times volume. And then minus the buoyant force, that's going to be the density not of the metal but of water, because this is, remember, the weight of water displaced times the volume of the cube times g. Okay, so we have common factors here, volume times g. So this is the density of the metal minus the density of water times g times the volume. And the volume is 2 meters times 2 meters times 2 meters. Okay, so it's the difference in the densities, but volume times g. Volume is 2 times 2 times 2, g, so those are common factors. All right, and so then we can plug in, and we can see that this is going to be 4 times the density of water, because the density of the metal is 5 times the density of water, times g, times 8, and that'd be cubic meters. Okay, and so that gives us 8 times 4 is 32 g, or 320 times the density of water, times 4 is 32, times 10 is 320, density of water is 10 to the 3 kilograms per meter cubed, and so this gives us 3.2 times 10 to the 5 newtons for the apparent weight. Now how does that compare with the true weight? Well, the true weight is going to be equal to the density of metal, so that's 5 times 10 to the 3 kilograms per cubic meter times g, 10, times the volume, 2 times 2 times 2 is 8, so that's 420. And then this is 10 to the 3, 10 to the 4, 8 times 5 is 40. That'd be 4. That's times 10 to the 3, or that's equal to 4.2 times 10 to the 5 newtons. I think that's right. 5g times volume, so that's 8 times 5 is 40, times 10 is 420, times 2. Good. Okay, so that's our true weight. So our apparent weight then has decreased by this factor over our true weight.